continuation of the previous class. Here we are looking for the definition for the term the electron mobility. The symbol is mu. It is given by the equation Vd divided by E. It is the ratio of drift velocity to electric field. The electron mobility in the conductor. For a simple definition, we can write this equation as put E equals 1, unit value of E, U becomes Vd. Now the definition is clear. Electron mobility is drift velocity under unit electric field. Under the electric field of unit value, whatever the drift velocity of the electron is same as electron mobility in the conductor. The SI unit for the electronic mobility, we get it from this equation, because write the SI unit for velocity. It is meter per second. Write the SI unit for electric field, Newton per coulomb. Simplify. Meter, coulomb per second per Newton. SI unit of electron mobility in the conductor. And the next is Ohm's law. As you know, Ohm's law is equal to V, that is equation, defined the equation, V is equal to Ri. Says the potential or the voltage applied across the conductor is directly proportional to the current flowing in it. And this R is called as proportionality constant. Equation says voltage and the current are directly proportional with each other, and they are electrical resistance of the conductor which remains constant over the possible values of all possible values of V and I. That is a mathematical form of Ohm's law. It can be represented also in the graphical representation of Ohm's law. If you put this equation in the graphical form, we get a graph like this. That is V on the y-axis, I on the x-axis. Because values of V and I are measurable. That is, voltage is measured by voltmeter and the current is measured by ammeter. By connecting these instruments into the conductor, we can measure the values of the potential or voltage difference applied across it and the current flowing in the conductor. When we draw the graph between the values of V and I about the conductor, we are get accordance to the equation, it should be a straight line. Straight line means linear relationship. These are, that is, the relationship between them is a straight line. There is a linear relationship between V and Y, E and V and I, straight line. So for straight line, slope remains constant at all the points. Slope is equal to R. that is a resistance, electrical resistance is a constant at all the values of V and I. That is a straight line says that graphical representation of Ohm's law, mathematical representation of Ohm's law. This is says that this is Ohm's law. We can verify this Ohm's law for the materials we are using. Materials are electrical conductors. As you know, electrical conductors are very good conductors, very low conductors, semiconductors like this. When you do so or verify, let us verify experimentally, and we see that when we draw the graph between V and I, we get three different graphs. This is a graph, what is that? Straight line shows is an ideal or Ohm's law. But here, the graph here straight line, till then straight line, then it is getting deviated. No linear relationship. No straight line, it is a curve like this. For all the good conductors, all electrical, all good conductors of electricity. Example, copper, aluminum, like that. And it says that for the conductors like this, Ohm's law is applicable up to a certain limit, up to a certain voltage range or current range. Beyond that, that is higher voltage, higher current, the law is not applicable. The material does not obey Ohm's law. That is deviation. Shows that at higher values of V and I, that is conductors also they have changed their resistance. Resistance of the conductor changes as well. It is because of change in the resistance. That is deviation from the Ohm's law. But it is there up to this. So where you see that Ohm's law is not applicable for all good conductors or metallic conductors. At high values of voltages and current. And let us verify the Ohm's law for a material like this. Look at the material is an alloy. This alloy means gallium is a metal, a symbol, arsenic is a metal. But you are taking the alloy of the material, that is mixture, solid, and alloy of this metal. When you verify this Ohm's law using this graph, but graph here what is interchange, of course, I and V are interchanged. Whether it is interchange or it should be a straight line from the Ohm's law. Look at this, you get a graph like this. Look at a lot of difference here. Here straight line, okay, Ohm's law, but very short range, that is very lower values of V and I, it is obeyed. But a long range, that is little higher values of V and I, so Ohm's law is not applicable. A complete deviation, not a straight line, curve like this, Of course, increases, then decreases. This positive, positive deviation, negative deviation. Decreases with increase of voltage. This curve indicates that in this material, electrical resistance is not constant. Electrical resistance also variable with variation of V and I beyond this value. That is variable. That is materials whose resistance is variable with voltage and current, where Ohm's law is not applicable. Non-ohmic conductors. Here ohmic conductors. Difference. This is a deviation. Where you see that is limited. Ohm's law is not applicable for these materials. One more set of materials. The material is, what is that? Non-metallic materials. Non-metallic materials means silicon and germanium. because you have heard of silicon and germanium, they are semiconductors, materials of semiconductors, making diodes and transistors. In that materials, when you verify that Ohm's law require that I and V, we get the curve like this, again non-linear curve. So that Ohm's law is not applicable, and resistance of this also varies with the variation of these because non-linear. This is verified, that is current values and is verified by applying the voltage in reverse direction as well. That is forward bias, reverse bias. Voltage is reverse. We see that current is almost, what is that? Current is almost nil or very small amount of current flows when we reverse the potential. But these two conductors are, what is that? Bilateral. Current flows in both the directions. But this material is unilateral. Current flows in only one direction, not in other direction. These are current flowing, what is that? One direction. Other direction current does not. But its current is very small amount of, because the scale is microamp. The scale is milliamp. Different scales are used. Here the voltage, negative voltage, positive voltage. Says that it indicates the characteristics of the diode. This is what it is. This also a not straight line, very small current or no current. No linearity, no linearity. Ohm's law is not applicable. Showing that Ohm's law, the material does not obey the Ohm's law. This is about the limitations of the Ohm's law. Now next is resistance. This rho is called as resistivity of the material, that I taught in the previous class in details. Resistivity means specific value. Resistance means general term. This resistivity is of a material is a temperature dependent. If the temperature of the material changes, resistivity of the material also changes. Resistivity either increase or decrease. We have different types of materials, conductors. It may either increase or decrease. Now you can see what is the effect of temperature on the resistivity. Let us understand by studying the experiment, and in the graphical form we can understand what is the effect of temperature on the resistivity. There is a mathematical equation for the resistivity. Recall this resistivity equation. M divided by this N into E square, that is P. M stands for mass of electron and N stands for number of electrons. What electrons? Free electrons, which accounts for the electrical conductance. Number of free electrons per unit volume of the material, and this is the charge of the electron. This is a relaxation time. So this is a relaxation time, but thermal that is only in the thermal condition. These are related. And this resistivity, look at that, these are constant for the electrons, these are, what is that, variable. Let us verify the effect of temperature on the resistivity for a good conductor, electrical conductors or metallic conductors like copper, aluminum, nickel, chrome, like this. Look at this, in very good conductors, any metallic conductors, the value of N remains almost same, unaffected, because the free electrons, it is given one time only, and these metals are non-ionizable by the effect of temperature. It is produced once for all, and no further increase in this, no further giving of free electrons to material, by change of temperature. That is remains constant with a variation of temperature. This remains constant in good conductors. Only thing, this is a variable with temperature. Let us see how does this relaxation time varies with temperature. Look at that. What is relaxation time? This electron. The electron is moving by thermal energy or IR radiations. This electron here commencing from what is at zero velocity and move towards other atom or kernel, moving from one kernel to other kernel, adjacent kernel. Electron, what is that? Gains energy. That is gains velocity, increase in velocity, that's thermal velocity. This thermal velocity increases if temperature increases. So speed of the electron, what is that? Effect of temperature on the material will increase the speed of the electron between the two adjacent kernel. Here 0 and increases to a maximum value. Speed increases, or the faster it moves from this kernel to this kernel, this, that is relaxation time, reduces. Lower is the value of relaxation time. So with the increase of temperature, this T velocity increases, T decreases, relaxation time decreases. So faster, that is reduces the value. As temperature increases, T decreases. Look at that. This rho and T are inversely proportional, inverse. As it decreases, this should increase. So this equation says that with the increase of temperature, that is resistivity increases. That is shows that graphical representation. Experimentally, when we verify this, resistivity is determined at different temperature. You can take on that and draw the graph between the resistivity and T. T temperature is taken in Kelvin scale. Draw the graph between them, you get a graph like this. This is of course not a straight line. It's a curve. So it is an increase. Resistivity increases with temperature. For what is that? Good conductors they produce copper and aluminum like this. Graphical. So accordingly equation says this increases with increase of temperature, and experimental evidence says that resistivity increases, it increases with increase of temperature, of course in the curve. And the same thing is verified with another alloy, that is a nickel chrome alloy. Nickel is a metal, chrome is alloy. When you take this in, of course it increases, resistance increases with increase of temperature, it is a straight line like this. In both these, what is that, metallic conductors and alloys of metal, resistivity increases with the increase of temperature. Experimental verification and it is equation, theoretical verification. Both are correlated. Let us take the material, other material, non-metallic, or semiconductor like this. Semiconductor is either silicon or germanium. What is the difference between the non-metal? Difference is these atoms are ionizable with the effect of temperature. Here, these atoms are not ionizable with the effect of temperature. Here, in case of semiconductor, the same equation, resistivity, this N is the number of free electrons. At room temperature, number of electrons are very few. Very few atoms of the material can produce what is give free electrons. Very few electrons are available in material. These free electrons increases upon increase of temperature. Upon increase in temperature, more and more atoms undergo ionization, giving more number of free electrons. That is the nature of the atoms, like silicon and germanium. So here, with the increase of temperature, N value increases in quite a large value, but a higher value. Value of N increases with increase of temperature. And what about the relaxation time? Relaxation time, this decreases, same concept. Whatever decrease with the increase of temperature, also same effect here in the semiconductor also. But difference here increase, decrease, but not getting compensated. This increase in value is predominates over decrease in T. The increase in value is quite larger than the decrease in T. As a result, overall the denominator values increases with increase of temperature in case of material like this. So as the denominator value increases, resistance value decreases. Therefore, resistance of that material decreases with increase of temperature. Experimental verification says that this is the curve we get. The curve also get the same idea. Resistance decreases with increase of temperature. That is a curve like this. So now resistance value in this graph, we taken this in SI unit, that is ohm meter, and temperature value taken in Kelvin like this. So that effect of temperature, on the resistance or resistivity of the material. And one more term you come across here, the term is alpha. It is called as temperature coefficient of resistivity. You need to understand the definition for this term. Temperature coefficient of resistivity. This is the mathematical equation for any conductors. That is, resistance conductor is variable with variation of temperature. The resistance, that is variation, change in resistance is directly proportional to the resistance of the conductor into change in the temperature. More change in temperature, more change in resistance. Also depends on the magnitude of the resistance, initial resistance. That is a differential form. So when you remove this proportionality relationship, equals constant. Look at this. This constant is alpha. This is proportionality sign. This is called temperature coefficient of resistivity. So this is the equation, differential equation. Let us write in integral form. Integration of left hand side, integration of right hand side. Integration means initial value, final value, temperature initial value, final value. Integrate this and get this value. dr is r, apply limits. These are constant, alpha into r, that is taken as initial value r1. And dt means T2 minus T into T2 minus temperature value. You can write this as, that is delta r, delta T, r1. Alpha is equal to, write this as delta r by r1 delta T. What is alpha in terms of resistance? So temperature coefficient of resistivity is rate of change of resistance with temperature with respect to its resistance. Rate of change of resistance with temperature. So what is the increase in resistance with increase in temperature with respect to the initial resistance? What is? That is the temperature coefficient of the resistivity. Now it is in terms of resistivity also you can write the same, because resistance and resistivity are directly proportional. So this is same as, it will replace this. Both sides we have, therefore you can write resistivity, that is initial resistivity, final resistivity, initial resistivity, temperature, temperature. It is a rho is the resistivity of the material when temperature is T1. Rho 2 is the resistivity of the material when temperature is T2. And alpha is the temperature coefficient of resistivity. It is the same equation is. So resistivity, in terms of resistivity, rate of change of resistivity with temperature with respect to resistivity. That is the definition for the temperature coefficient of resistivity. So how much resistance or how much resistivity changes with the change of temperature. This alpha is it may be either positive, negative or 0. Positive means if alpha has all positive values means this resistivity is always increasing with temperature here. Negative means it decreases with temperature. Alpha equals 0 means remains constant. It increases, remains constant. Resistive value. This is about the semiconductor materials or non-conductors, metals, non-metals. These are terms. These are very important terms. Next is electric power dissipation. Now we have a conductor. What is meant by electric power dissipation? Let us understand it and see how we can able to understand that electric power dissipation and its importance. This is an electrical conductor. Here the point is initial point, the final point. Across this conductor, the potential difference is applied. V1 is potential, V2 is a potential. A higher potential, lower potential. V or delta V is the difference in potential. Due to this potential difference, electric current flow in the conductor. That is the amount of electric current. So you know that electric current is flowing from always higher voltage, higher potential to lower potential. It is quite natural, spontaneous. Electric current is always flowing from higher potential to lower potential. This is a higher potential value, lower potential value. Current always flows spontaneously. If this is the direction of flow of current, what is the direction of charge? That is electron, the electron conductor. The direction is opposite. Choose the charge electron. Electrons are moving in this, are flowing in this direction. This says that the current definition, that is, they define current in terms of, that is, a transfer of charge. So, the rate of flow of charge with time, that is dq by dt. So, rate of flow of charge is the current strength. This is a definition. Recall this equation. Last class I defined this equation. You read this equation as dq is equal to I dt, same equation, call it as equation 1. So this is required, remember this equation. This is the initial point and final point. This is potential. Let us estimate what is the potential energy at this point, that is the electric potential energy. Electric potential energy is given by U. Definition says electric potential energy at any point U is equal to electric potential into charge. Remember the definition. Recall this from the electrostatics. Now, from year to year, when the current flowing from year to year, there is always a change in the electric potential energy. Potential energy decreases. What is the change in electric potential energy? du from year to year. Difference in potential energy, final minus initial potential energy. Substitute for this. So this V is delta V or V, you can take it because most of the times delta V is taken as V, potential difference applied. So the potential here V2 minus V1 potential is this one, and since it is du, dq becomes dq. This is delta V or V. I told you. D is equal to minus V into dq. Equation reduced to this form. That is a change in the electric potential when the electric current flowing from here to here. This is negative value because the difference here V2 minus 1, this higher value located, this higher potential, lower potential. Negative value says that this negative indicates that the potential energy change, that is decrease. Potential energy decreases. Electric energy losing. Electric energy, what is that? That is there is a decrease in electric energy from here to here. Where the electric energy goes? Come to this point. When the electron is moving from this kernel to this kernel, now I am talking about not thermal energy. It is electron flow, electron movement by the effect of voltage or electric field. Here this velocity increases. What is that? Velocity and acceleration. Velocity increases by the effect of electric field. So what happens in the electric field? Velocity increases, but the drift velocity in material is maintained steady increase. There is always constant. So this Vd is the one we are using for measurement of I. This remains steady, but V says that V increases. What is the velocity of this electron? Electron velocity, it is due to potential, not by thermal. Thermal is here. Where that energy, that is velocity, that is in terms of kinetic energy, goes. So electron, after colliding here, electron will increase its energy. What energy? Kinetic energy, moving faster. So this kinetic energy, because this remains constant, so from here to here, kinetic energy of the electron increases by the effect of voltage. This increase in electron, the kinetic energy, what happens? It comes here and collide it. It will give the excess kinetic energy what is gained to this kernel. As a result, the collision, the energy is transferred from electron to this kernel or atom, which is getting more oscillated or vibrated about its position. So now what happens? That electric energy, potential energy, it is appear in the form of kinetic energy. Now after collision appear in the form of vibrational energy of the lattice atom. So all atoms, what is that? Vibration increases. So it is excited. So excited will not remain over, it is come back. So it will go back after losing energy. What is that? That energy what is gained in the form of heat radiation or IR. So IR is emitted. So that is in the form of heat is emitted. It will go back. Now look at that. Finally, the electric energy change into kinetic energy of electron, and then vibration energy of the crystal, and then into heat energy or IR radiation emitted. Therefore, temperature of the material increases. Effect of temperature. Look at this. This is a procedure, or it is a phenomena taking place in the conductor when the electric current is flowing. Finally, what happens? This is same as decrease in potential energy is increase in kinetic energy, same as this. So electric energy has become finally heat energy and is dissipated as was a waste. Energy is dissipated, energy lost. What electric energy is lost? In terms of power, if we calculate, what is the electron power means rate of change of energy with time. That is the amount of energy change into heat. This amount of energy, whatever, mathematical derivation. This one substitute for this. When you substitute this, dt cancels, vi remains. Finally, look at that final equation. PD stands for power dissipation. What is meant by power dissipation? Some amount of electric power is dissipated, will go as a waste in the form of heat. The temperature increases. That is unavoidable in all conductors. This is a given by, so the power dissipation is given by the product of the voltage applied across this and the amount of electric current flowing into this, flowing through this. This is a go as waste, unavoidable. That is called power dissipation. Electric power dissipation is there in all conductors where the electric current is flowing. Now come to this point, very important. Let's understand this point. Let us write this equation, that is in terms of V is not using Ohm's law. Right? I no, in terms of only I, that is V is equal to IR, Ohm's law. So I square R in terms of only I or in terms of only V, we get this. So these are the same equations. Here in terms of V and I, it is in terms of I, it is in terms of V only. This is the equations we use. And important is, let us look at this equation. Electric power dissipation in the form of heat, I square R. So this equation or phenomena is used for the what is the construction of a device known as electrical heater. We are using it home appliances. Electrical heaters, boilers or electrical heater, electric stoves, electric heaters, converting electric energy into heat energy. So what is the criteria required? We need a conductor. What is that? Conductor of high resistance. If you have high resistance, more amount of electric current becomes heat. And the conductor to which if the current flows higher value, that is I square. If I square means square. So it becomes what is that? Quite a large amount of electric current becomes heat. That is why. So electric heater is always what is that? Material choose for making electrical heater is a material of high resistance. That is one point. And also we have what is that? There is a provision for passing more what is that? More amount of current. So the device is designed for flowing more current through the conductor. If more current flows, more heat. So more power becomes more energy. So in the electric heater, we are using this equation. This application finds this. That is why electric heaters are made on this. And one of the more important applications. Yeah. This is a conductor. Let us see that. Here in case of power transmission. What is power transmission? Electric power is generated at one place and transmitted to other area where we require distribution of electric power to homes, industries and commercial establishments. Let us say it is a initial point at which electric power is generated, source of electric power generated. You know that there are different types of sources of electric power generation. Just I'll brief it. Thermal power, by converting heat into power, thermal power station. Wind power station, converting heat, that is wind flow into electric power. Solar power, solar light into electric energy. And hydro power, hydroelectric power, that is water flow under pressure, converting into electricity, hydroelectric power generator. And nuclear power generator, nuclear energy into electric energy. There are different types or sources of electricity generator. So this is a point where area is electricity is generated. So from this point of generation, we are sending or transmitting electric power to other area point where the distribution is taking place. If you apply whatever the power generated into this conductor, is a conductor, so there is no aluminum wires, the tension wires. See that this is applicable. Even though aluminum wire is low, less conductor current, no. A lot of energy, that is power, electric power, go as waste in the form of heat. Power dissipation while the current is flowing. That is unavoidable. But look at this, very important. Can we able to minimize that loss of power? It is possible, but one has to think about into this concept. Here, look at this. That is P is equal to same equation, Vi or I into V. That is power. This is power dissipated. Now this power is generated. Here, what is the P? The total amount of power is generated. Electric power is generated. When you put it across this is our I into V. And power dissipated is this. So this, don't confuse it. This P stands for total amount of power generated. Among it, a fraction of it, what is PD, dissipated or go as waste. This is the equation. Put this equation into this equation. Let us see that. Very simple mathematics. I is there. What is I? Write the equation as P by V. I is equal to P by V. So I square is there. P square by V square. Look at this equation. One more equation. Very most important equation. Now PD is equal to P square R divided by V square. Look at this quantities on the right hand side. What is P? Total amount of power generated. This power goes waste, PD. And R by V square. So these two, look at this R and V square. That is, R means by using the material, what is conductor materials of low resistance, that is lower the value, lower the PD value. We can reduce the power dissipation. One thing. That is why we always look for the materials which have low resistance. That is aluminum wire. There are two effects. That is aluminum has two benefits. Aluminum wire is cost effective. Price is low and resistance is there. Therefore, aluminum wires are used for the power transmission. That is one concept. And also most important is V square. What is V square? The potential difference applied across this. V square, it is not V. If you increase the potential difference, that is higher the potential difference, lower the value. Very higher the potential difference, very lower the value. That means by increasing, what is that? By applying a very high potential difference between the 2 points for the transmission, we can minimize the power dissipation as much as possible. That is about 30% or about 5% like this. So that is why the power transmission lines have been constructed with very high voltage at the generation, very low voltage at the distribution point. What is the expected voltage you are producing here? We can produce minimum of 11 kV and also 50 kV and also 500 kV. What is 11 kV? 11,000 volts. 50 kV means 50,000 volts. 500 kV, 500,000 volts, very high voltage can able to maintain. We can produce at this point. How can you able to produce? Question is that generation is the power generation. You have to produce that because depending on the amount of power generated, we can have what is that potential 11 kV, 50 kV and 500 kV we can produce at this point. How it is possible? By again man-made device, transformers. What are transformers? There are two types of transformers. Electrical transformers. These are big electrical transformers. What is the function of those electrical transformers? There are two types. Step up, voltage step up transformers and voltage step down transformers. What is voltage step up? Small voltage into big voltage step up. So depending on what is that, the bigger transformers. Here at the power generation station, we see that a bigger transformers. What type of transformers? Step up transformers. What is the power generated? Is stepped up to 11,000 kV or 50,000 kV or 500,000 kV depending on the amount of power generated. Here by using transformers. Here transformers of what is that step down, because high voltage now. From high voltage to low voltage you are using here at this point transformers, step down transformer 11,000 or 50,000, 5,000 into 4,000 kV. That is 4,000 kV. No problem at the distribution point. Here. Using transformers of what is that? Step down transformers. So these are the using these devices, again man-made devices. So the voltage is increased very high, voltage is decreased because high voltage difference avoid power dissipation. These are what is that? Electric, that is power transmission lines. Now 11,000 kV line can be laid underground, say of course now line underground 11,000 kV, but the voltage now what is 50 kV or 500 kV voltage, it is not safe to lay underground. It's quite dangerous. But overhead, above the surface they are, but in the atmospheric air of course, using what is that? Aluminum wires, high tension wire. That is, so you are using always overhead power lines for the transmission of power above 50 or 500 volt to that. So this high voltage, what is that? Tension, high tension wire, usually what is that? High voltage lines produces quite a what is that? Quite a large amount of electric field. Because of electric flow, there is also magnetic field. Strong magnetic field, strong electric field is surrounding the conductor. Very strong. It is quite dangerous for living beings. So these electric lines are always what is that? Kept away from the populated areas. No building construction or home constructions are in this. So even though what is that? If the power to minimize that strong electric or magnetic field, you know that strong electric magnetic field on the living beings produces undesirable diseases. So it is always what is that? Kept at a height of more than 20 feet or 30 feet to avoid what is that? The distance, to avoid the strong magnetic field, because strong magnetic field strength decreases from the point where it is generated. It is safe to have what is that? Any high tension power, always lines is kept from the above, from the height of above, from the ground above 20 feet or 40 feet better, to avoid exposure to strong electric and magnetic field to living beings. And it's not safe to have any houses or what is that? Working under high tension lines. There are, but still what is that? In the city areas, most of the BBMP parks have been formed under electric lines. You are working under it today. Every day I am working under electric lines in the park, because all the parks are made under the electric lines. Unavoidable. That is one way. And also it is also dangerous if during rain, what is that? gives a spark very big to fire if there is any short circuit at that voltage. So a lot dangerous this electric lines, but you have to kept safe away from the populated area. So that is the one we understood the concept. Very important is high voltage, because remember high voltage not for transmission. Transmission is there at the same velocity. High voltage to minimize the power dissipation, to minimize the loss of electric current what we produce at the generation. That is the one. So this is the concept. What is that? Power dissipation concept. We are finding that in making electrical resistance and also in the power transmission. So with this the concept is finished. Thank you very much.